Well, here's another example of uniform circular motion, and that's the behavior of objects in orbit. A satellite around the Earth, the moon around the Earth around the sun. Um, like all of these things are examples of uniform circular motion. The only difference is that in this case, instead of it being the tension of a string that's keeping an object going in a circle, it's the invisible force of gravity that connects those two objects together, and it's like you know, um, it's kind of like the satellites going around the Earth. They behave as if there were a string attached, and that string was, you know, uh, tight, and it was swinging around and around and keeping that object in uniform circular motion. But there is no string. There's an invisible force that connects the two of them together. So the way that happens is it's the force of gravity. Now, we've looked at the force of gravity in 2204, and we had this equation that the force of gravity is equal to mg, which is mass, and then this piece is the acceleration due to gravity, which is 9.81 meters per second squared. Well, that's kind of like a shorthand version. This is a like a compressed version of the actual formula for the force of gravity, which is this one over here. So this is an equation that Isaac Newton came up with to describe why the moon stays in orbit around the Earth, why the planets are in orbit around the sun, and he even theorized that it was possible for us to put artificial satellites in orbit around the Earth. So this is the full equation, and you can see here, I don't know if it makes sense. Let's look at all the individual pieces here. The big M would be one mass. The small m would just be another mass. And, usually they're two different sizes, and that's why the two m's are different sizes. Like it could be like the Earth and the moon, or the sun and the Earth. So one is bigger than the other, and generally, it's just a convention. You could say M1 and M2 if you want. It makes no difference. It's just I have them in the equation here as two different size m's because normally there are two different size m's. And then the r, that is the distance between the centers of mass. So if this is our big M and this is our small m, then this would be the radius. It's the distance between their two centers of mass. You don't go from surface to surface. You go from the center of mass of each one, and that's how the force of gravity acts. So according to Newton, there is a gravitational attraction. It is mutual. So you're going to have a force this way, and there's going to be a force this way. So there is a mutual attraction between them. Just like if you have an object being whirled around on a string, the tension acts in both directions. So there's a mutual attraction. The force of gravity acts in both directions like tension. Whatever the force of gravity is on one, the exact same force of gravity occurs on the other one, just in the opposite direction. This is an example of Newton's third law. So it acts in both directions like tension. This is an example of Newton's third law. For every action, there's an equal and opposite reaction. Well, if you look at the form of the equation here, you can see that as if we double one of the masses, the force of gravity will double. If we double the other mass, the force of gravity will double. There's a direct relationship. If you increase either of the masses, then the force of gravity will go up by the exact same amount. So I'm going to redraw that equation down here so I can talk about it. So there's the force of gravity. There's a great big old G. I'll get to that great big old G now in a second. GMM over R squared. And you can see that if the M doubles, the force of gravity doubles. Or the small m, so either one of them, if they double, the force of gravity doubles. But if R doubles, then the force of gravity is 1/4. It is going to vary with the inverse square of the radius. If you triple, then the force of gravity is 1/9. So whatever you do to the radius, you turn that upside down and square it. So doubling the radius, the force of gravity will only be 1/4 as strong. If you triple the radius, the force of gravity will only be 1/9 as strong. So the force of gravity decreases with the square of the radius. It decreases with the square of the radius. That's the conclusion you come to. And you might be wondering to yourself, why is that the case? So why did that happen? Well, it has to do with the fact that if you look at some kind of body like this, here's M, and apparently it's, according to Isaac Newton, it's generating a force field, and that force field is spread over the surface of a sphere, and that does not look very spherical, but just bear with me. So the force of gravity is spread out over the surface of a sphere. And if you increase the size of that sphere, so if a sphere doubles in radius, the surface area is 4 times as much. Right? If you have a sphere with R, the surface area is 4 pi R squared. Now, if you double that R like this, if that's 2R, then here's what's going to happen. The surface area will be 4 pi times 2R squared, which will be, here the 2 is going to square, 4 times 4 pi R squared. So the surface area will be 4 times, this is the original. And if we make our sphere even bigger, if we do this, and let's say this is 3R, then the surface area would be 4 pi times 3R squared, which is, square that 3, 9 times 4 pi R squared. So you see what happens. Every time if we change the radius, we end up with a sphere that is the square of that radius bigger than the one before. Doubling the radius gives you 4 times the surface area. Tripling the radius gives you 9 times the surface area. Well, it's kind of like blowing up a balloon. So let's say, if this were a balloon, so just imagine, I don't know. Imagine this was a red balloon. And so I'll color that in red. Okay, so when the balloon is this size, it's going to be very deeply red, right? It's got so much red dye in the balloon. But when you blow it up to twice as big, it's the exact same amount of red dye, but it's spread out over 4 times as much area. So now it's the exact same amount of red dye, but the color has been diluted. It's not nearly as red as it was before. It's kind of pink. And if you triple the radius, now it's still the exact same amount of red dye, but it's spread out over 9 times as much surface area. So you can think about the gravitational force as being like the amount of red dye in a balloon, and you can keep blowing it up and blowing it up and blowing it up. The amount of red dye is never going to change. It's just going to dilute. You're not losing any red dye, but what you're losing is the intensity. It's going to decrease as you get bigger and bigger, a bigger and bigger, bigger balloon. It'll start off deeply red, and then it'll kind of like start fading, and then it'll eventually be pink, and then very, very light pink. So it's the same thing that happens with gravity. When you increase the surface area, it's the same amount of force, but now it's spread out over a much bigger surface area. The amount of red doesn't change. But gets spread out over more surface area. And this is the same thing that happens with force. So the same thing happens to the force of gravity. It's proportional to 1 over r squared because the surface area is proportional to r squared. That's the reason. The force of gravity is like the amount of red in this balloon. When you double the radius, you're quadrupling the surface area, and now the same amount of force is spread over 4 times as much area. Same thing if you triple it. Now you've got 9 times as much surface area, and the force of gravity, it's the same force of gravity, but it's been diluted. It's spread over a much bigger sphere. So I'll just go back up here again. You can see, so when the r doubles, the force of gravity is only a quarter because there's 4 times as much surface area. When you triple the radius, the force of gravity is 1/9 because you have 9 times as much surface area. Well, hopefully that kind of helps explain why the equation has this form. It's just a geometric property of the fact that we're dealing with 3 dimensions, and the surface area of a 3-dimensional sphere is related to r squared. Well, the last thing to look at here is what is this g business? You can see this great big G in the equation. The G, that is the universal gravitational constant. And it's the reason it's put in there is because, well, we need it because the units we use, like kilograms, meters, newtons, these are kind of random things. We made these things up. These are invented quantities. They are invented quantities, and they're, we could have anything here. We could use any unit for mass, any unit for length, any unit for force. But we've created these units for force, and in order to make our proportionality, the force of gravity is proportional to mm over r squared. In order to make the kilograms times kilograms, meters squared, newtons, to make all this fit together, we need to insert what's the word? Oh, well, it's something that makes both sides of the equation fit together. This makes the units correspond to each other. This makes the what's happening on the right-hand side turn into newtons. They're invented quantities, and so the G makes them correspond. If we were using a different system of measurement, the G would be different. So there are different measurement systems. Like if we weren't using the metric system, this number would be completely different. And by the way, it's 6.67 times 10 to the negative 11. That's what we need. It's 6.67 times 10 to the minus 11. And let me see here now. 6.67 times 10 to the negative 11. Oh, I need to... for a second. It's right at the front of the textbook somewhere. All of the constants. Meters cubed per second squared times kilograms. Meters cubed times second squared. No, per second squared times kilograms. Well, I mean, the only thing that I ever remember off the top of my head is this, 6.67 times 10 to the negative 11. The units, they will just cancel out and leave you with newtons. That's the whole point of this. So it's 6.67 times 10 to the negative 11. And we can calculate the force between two objects using that equation. Well, let's have a look at this. What if we have a satellite in orbit around the Earth, maybe that satellite is 100 kilograms, and the satellite is, the radius is I don't know, maybe like 500 kilometers above the surface. And the question would be, what is the orbital speed? How fast is it going? Well, here's our situation. We have the Earth. That's going to be a great big old mass. And then here's our, that's too much. And then here's our satellite. And that's the radius of the Earth. So this piece here is 500 kilometers. But then we have the radius of the Earth as well. So the total radius is going to be the radius of the Earth, and we have to turn that into meters. The radius of the Earth is 6.38 times 10 to the 6 meters. And then we have to add on the 500 kilometers, which is 500, and each kilometer is 1,000 meters times 10 to the 3 meters, because it's from the center of mass and not from the surface of the Earth. Our gravitational force is always measured from the center of mass. 6.38 exponent 6 plus 500 exponent 3 is 688 times 10 to the 6 meters. And there's only one force that's keeping this satellite in orbit around the Earth, keeping it going in a circle. Our free body diagram is going to look like this. Here's our small satellite, and the force of gravity on it is going to be just the force of gravity. That's what's going to keep it in orbit. That's what's going to keep it going in a circle, just like the tension on a string. And then our F net equation is going to be F net is equal to the force of gravity. It's the only thing that's keeping this satellite going around the Earth. So I'm going to have to come down here a little ways. If I click this, that's not what I wanted to happen. So now we have mv squared over r, that's the F net part, is gmm over r squared. So this equates the centripetal force to the gravitational force. This is your centripetal force. That's the F net part. And this is the force of gravity part. And this equation is going to be true. This is going to be universal for all orbits. If you have an object where some small mass m is orbiting some big mass m. So here we have a small mass m orbiting a big mass, right? There's your satellite, and there's the big mass. Now, the cool thing about this is we can get rid of some things. Look at this. So here you can see that the mass of the satellite is irrelevant. It doesn't matter how big the satellite is. Just like something falling towards the Earth, right? If you throw something in projectile motion, it doesn't matter how massive it is. The path that it takes is independent of the mass. And the path of a satellite is independent of its mass. It only matters where it is and how fast it's going. You can also see here that we have, there's an R here, and we can cancel one of those R's out. And let's see what we got left. Over on this side, we only have the V squared left. Over on this side, we have a G, the big M, which is the mass of the Earth or the whatever is being orbited, all over R. And we can take that one step further and say that the orbital speed is equal to the square root of gm over r. And this is an equation that can be used to describe the motion of bodies in orbit around some other large satellite. So now we know the radius. We had to measure the radius from the center of the Earth, not from the surface of the Earth. You always have to measure it from the center of mass of the object that's being orbited, and to the center of mass, obviously, of the satellite too, but the satellite is so tiny that it doesn't really matter. The surface of the satellite, the center of the satellite, they're virtually the same thing, but the Earth is different. The Earth is so large. So now here's all we got to do. The orbital speed of the satellite is going to be the square root of g, 6.67 times 10 to the negative 11. This is what it looks like on my calculator instead of saying times 10 to the power up. The mass of the Earth, I have a table up here where we can find that. 5.98 times 10 to the 24 kilograms. This method just kind of keeps things nice and short. And the radius is going to be 6.88 exponent 6. And this is going to give us the orbital speed of a satellite placed 500 meters above the Earth's surface. 6.67 exponent negative 11 oops, forgot my root sign, 6.67 exponent negative 11 times 5.98 exponent 24 divided by 6.88 exponent 6, and I get 7614. So let's round it up to 3 digits. 7610 meters per second. So that's how fast a satellite in orbit around the Earth would be going at 500 kilometers above the Earth's surface. And if you want to change that into kilometers per hour, it works out to 27,000 kilometers an hour, or 27,400 kilometers per hour. So just 7.6 kilometers per second. That's the rate at which it's going to whirl around the Earth. And so here's our Earth. There's our satellite, 500 kilometers from the Earth's surface. And how long will it take to go around? That's another question. I asked you, what is the orbital speed? Now I can ask, so at this rate, what is the period, which is the time to orbit the Earth? Well, remember, the speed is equal to 2 pi r, which is all the way around, all over t. The t is 2 pi r over v. And we've already found the radius. It's up here, 6.88 times 10 to the 6. So now all I got to do is, this is going to give me my answer in seconds, 2 pi times 6.88 exponent 6. And the v we discovered is 7610. This is going to give me the number of seconds it takes for that satellite to orbit the Earth once. 2 exponent pi times 6.88 exponent 6 equals divided by 7610. And I get 5680. 5680 seconds to make one orbit around the Earth. Okay, so this is, I probably should have made this bigger. So here's my Earth. And there's my satellite in orbit around the Earth. It's got a V of 7610, and it's going around the Earth like this. And it takes 5680 seconds to go around once. Well, I'm going to divide that by, to get the number of minutes, let's divide by 60. So in minutes, that's going to equal, so 5680 divided by 60 equals 94.7 minutes. 94.7 minutes. So that's how long it takes. And you know what, folks? I don't know if you've ever heard this before, but that's how long it takes the International Space Station to go around the Earth. About once every 90 minutes. So this is right on the money. This has been calculated properly. So honestly, we went through a lot of kind of theory here. Let me just go back. Right, there's your equation for gravity. It is attractive between two masses that are separated by a distance r between their centers of mass. The reason that we have an r squared here is because of the fact that the force of gravity is spread over the surface of a three-dimensional sphere, and the surface area of a sphere goes up with the square of the radius, 4 pi r squared. And then when we equate those two things, we use our free body diagram. There's only one arrow in our free body diagram. Only the force of gravity is keeping our object in uniform circular motion, going around in a circle like this. That's the only thing that's keeping it going in a circle. So if that's the only thing keeping it going in a circle, That means that our F net equation is just, F net is equal to the force of gravity. That's it. There's nothing happening in the other direction. And then when we replace the F net with mv squared over r, and replace the force of gravity with the full equation, gmm over r squared, we can cancel out the m's of the smaller object that's doing the orbiting, cancel out one of the r's, and we get left with this really simple little equation right here that governs, and it tells you how fast satellites are going if they're placed at a distance r from some mass like the Earth or Jupiter or the Sun or whatever. And you can calculate how fast they're going. And then if you know how far away they are from the center, right? Because we have to measure, all of our r's are going to be measured from the center of mass of that object. So here we have the period, 2 pi times the radius, that's the circle, divided by v. We can get the number of seconds turned into minutes. And folks, this is right on. This is, that's all there is to it. I know that I could have just given you this equation starting off and say, here it is. But that's not how we like to do things in physics. In physics, people like to know where equations come from. If you're, if we do something in class and you're wondering, well, why, you should ask. And so I'm trying to address those why questions right up front. But there you are. V is equal to the square root of gm over r. That tells you everything you need to know about orbits. And honestly, now you can answer all kinds of questions about orbits. And end scene.